This always happens. As semester goes on, people get tired.
You should see in summer term.
What?
You should see in summer term. Nobody's here.
Okay. All right, I guess we will start. Yeah, the first thing is I've put up homework 2 online last week, and it's a bit more difficult than what you have been doing up until now. The first problem is relatively easy. You have to integrate this very simple ODE with forward Euler and with the Runge-Kutta second order, right? And compare the answers. But the second problem is actually it's repeated from one of your project problems. So I think this is the first problem in project 1. This time, though, you will do it with an implicit time integrator called Crank-Nicolson scheme. And you're given here how Crank-Nicolson scheme works. The right-hand side changes slightly. Is there a question?
No.
Yeah, go ahead.
Yeah, no question. I was just testing this for whether it's working or not.
Okay.
Yeah.
So, we're used to using the fully explicit scheme, where on the right-hand side, we only have Tn's, T at time level n. But with this semi-implicit scheme, we have a combination of Tn's and Tn plus 1's. Okay? So, you should start writing these things on paper before you actually start coding, because it's very helpful if you form the matrix that you need to solve first on paper. And it's exactly the same problem. You have to solve it up until steady state and compare your answer to the analytical solution. And if you remember, last time you were having trouble doing this with delta t 0.01. This time you will see that you can actually do the integration even if you set delta t equal 1 or even 3. But something will happen to the result, and you'll see what. Okay, so this is due in 1 week. Again, it's not, implementation is not very difficult. Just wrapping your head around the matrices, how everything is set up, might take some time. Come to me for help if you get stuck at any point. Okay, questions? All right. Okay, perfect. So, okay, so up until now, we've been sort of dabbling with very simple model equations. But they actually, today you'll see how everything ties together into solving the full Navier-Stokes Equations. So before that, let's do a bit of recap. And it's important that we go slow today because this is the heart of CFD. Okay? If you understand what happens today and maybe next class, that's all you need to know. Okay? Everything else is some sort of advanced version of what we'll see. Okay, so just let's just go through some very simple notation again. So we've seen this before. So if we have delta P, where P is pressure, you can see where which is a scalar. Okay, we can just write this as del P by del X. That's the I component, J component, and K component. Okay? But this is not the only way you can write this out. There's another way. You can write it out in matrix form as a vector. So it's del P over del X, del P over del Y, del P over del Z. And it's completely equivalent. We just switch to whichever form is most convenient for us. Okay? All right. Now, this is called grad P, okay? Or gradient of P. Beyond the gradient, we also know there's something called the Laplacian, Laplace squared P. Okay. And does anybody know what this Laplace squared P is equal to?
Del squared P over del x squared plus del squared x squared plus del squared P over del y squared.
Yeah, perfect. And in 3D, we just have the extra represented P by del z squared, right? So this is called the Laplacian of P. Laplacian of P. In vector form, this actually can be broken up as nabla dot nabla P. Okay? This is called the divergence. Again, you might be familiar with all of this. This is just as review, just to get everybody up to the same page. This is the divergence operator. Fine. So what is the divergence operator? So let's see. So let's see if we have nabla dot u. We know what that is? U is here, let's say, U is Ui plus Vj plus Wk. So U is the x, y, and z components of velocity all combined into one vector U. Okay? Nabla dot U is equal to Yes. No? Have you seen this before? Yeah, we have derived this, right? Yeah, you have seen this before. Okay. So, all right. If you don't remember, that's exactly where these matrix forms come in so handy. Okay. So, nabla.u you can write as, let's say, nabla becomes del over del x I plus del over del y j plus del over del z k. Okay, and this is being dotted with ui. All right. So I haven't done anything. I've just written the vector form in terms of partial derivatives. Can you tell me now what the answer should be?
Is this the del w over del y times
Del w over del y. Wait, so you're saying this should be
Del u by del x.
oh, right. So you were saying del w by del y.
yeah.
Let's see. Why would you say that? Okay, so let me
Is
see.
this a scalar?
Yeah, so if you take the divergence of a vector, you will get a scalar in the end. Just think of what A dot B is. A dot B gives you A1B plus A2B2 plus A3B2. Right? What were you saying? Go ahead. Oh, you were not saying it. All right. So fine. If we take the dot product of these two vectors, we just multiply the x components and then keep adding. So we get du by dx plus dv by dy plus dw by dz. Okay. So anytime you forget, this is the way to recover this. And even I don't remember most of this most of the time, so I have to fall back to using these simple techniques. Okay. All right. So Nabla.u, where u was the velocity vector, gives me this. All right, let's get back to this Laplacian of p. Okay, what about nabla squared p, which is actually equal to nabla dot nabla p. If I expand this, what would nabla be written as? This symbol is called nabla in Greek. So first, let's expand the first nabla, which is, all right, help me out.
Del over del x
Del over del x I
plus del over del y j plus del over del.
So yeah, again, nabla is what I had expanded it out. It's the same, fine. And we know gradient of p is
Del p del x.
Del square plus
No, del p del x.
right, perfect. Yes, del p over
Del x.
del x is the I component, and we have the j component, and we have the k component. All right, and then when we take this dot product, what do we get?
Del square.
Yeah, we get what we said the Laplacian looks like. Make sense? So anytime you forget any of these expanded long formulas, just go back to the basics and you can derive it very easily. Okay, so manipulating gradients and divergence and derivatives of a scalar is relatively easy. Pressure is a scalar here. With the Navier-Stokes, we have to do these things with the velocity vector. It becomes slightly more involved, but conceptually it's exactly the same. Okay, so let's see what happens. Okay, so let's expand out the expression for nabla u. Okay. And again, this is grad u or gradient of u. If we had pressure, this was a simple thing. Nabla p is del p by del x, I component, del p plus del p by del y, j component, and the k component. Okay. What happens now? Do you know what happens now? When we took the gradient of a scalar, the return was a vector. When we take the gradient of a vector, what happens? Do we get a scalar? Does it remain a vector?
Remain vector.
It remains a vector. So let's see. If we take the gradient, and u is three components, right? There's a u, v, and w. And we are taking the derivative in space. Nabla is derivative in space. So there's three variables I have to differentiate with: x, y, and z. So in total, we have how many possibilities?
9.
9 possibilities, right? So this actually is exactly 9 numbers. And it's the most convenient form to write it is a matrix. Okay. So this is actually written as, okay, we just take the first component of u, or the first row, del u by del x, del u by del y, del u by del z. Okay? You tell me, what goes in the second row?
Del v, del x, del v, del y, del v, del z.
Exactly. Del v del x, del v del y. And the third row is the same thing for the w component. So this is the most general form with no assumptions, no simplifications. This is exact. This is grad gradient of u. All right, now let's do something more complicated. How about we do the Laplacian of this thing? Okay, how should we do that? So if you already know the answer, forget about the answer that you know. Let's try to use the steps we just saw for pressure, but now let's do it for velocity.
So we multiply a matrix of 3 by 1 to this matrix.
Mm-hmm.
So it's 3 by 1 times 3 by 3 is again 3 by 3.
1 by 3 or 3 by 1. Right? Yeah, okay, but yeah, you're thinking about the correct thing. So first, I should decompose this as the what I wrote for the pressure, right? It's the same as nabla dot nabla u, right? And then we do exactly what you said. Okay. So we write this. Before that, let's see. If I say A dot B, okay, and a single underline means this is a vector, two underlines means this is a matrix or a second order tensor. Do you know how to write this out? So B is a matrix, right, with 9 numbers. Let's see. Let's say with 9 numbers. B is 3 by 3, it's 1, 1, B 1, 2, B 1, 3. B 2, 1, B 2, 2, B 2, 3. Yeah, 3, 3. Alright? And then, where does A go? A1, A2, A3. Where should they go?
It should be to the left.
So, all right, if you want to put it here, you want to multiply that way, right? Actually, we do it the other way. So this actually becomes this A1, A2, A3. Okay? And this, if you remember this very simple thing, you can convert any complicated vector formula into a simple expanded version. Okay. All right, so let's see. I said A dot B can be written as that. Let's see what looks familiar. B is a matrix, nabla U is a matrix, which we wrote up here. A is a vector. We said that this nabla term can be written as a vector, right? Fine, let's do that. Nabla dot nabla U is, all right. So what goes here? Help me.
So is del u over del x times del, that's times I, so is del square u over del x?
You are giving me the final answer.
Yes.
Now, go step by step, okay? So we said we will do a vector dot matrix thing, right? So let's write out the matrix first. So let's help me fill out the matrix.
Del u, del x, del u, del y.
Perfect. And then the other components go below that, right? So del p dx. If you get comfortable with what we are doing right now, you will never have trouble with vector mathematics again. So, all right, fine. That's our matrix. And what goes in here?
Del over del x I, del. Del over del y, del over del.
Everything good? All right, and now we know we just have to take a matrix vector product, which is, right, let's see. So what does it become? Somebody else, tell me. Anyway.
Del square, del
Del
square u over
square
del
u
x.
All right.
Del square u by del x square.
All right,
X
okay.
square.
And nothing else?
Del square u by del
So
y
that's
square.
plus del u square over del u y square. Y.
Now del y
Partial u squared.
Over C.
del y del z square.
Partial d squared.
So why don't you put y square?
And
No, del
Sorry.
this is square. And partial v squared over partial x squared, partial v squared, partial y squared.
Yeah.
Everything is partial squares with
Yeah.
the same matrix actually.
Exactly. But you see, it's relatively straightforward. Okay? We're just doing a matrix multiplication. We have a q dx times d by dx, which becomes the second derivative, plus this terms times that, which becomes the second derivative here, plus this times that, which becomes the third derivative, the second derivative here, third term. Okay? So that's basically first row times the column. Right? Next thing to do is second row times the column, and that's the answer that you guys were giving. So the second one becomes del 2v over del x squared plus del 2v y squared and the last one is the same. Okay, so you basically figured out what lambda squared u can be written as without memorizing anything. It's just very simple things. Everything makes sense? Any confusion? Okay, fine. This is nice. Why did we write this? Does this look familiar, this lambda squared u term?
Momentum.
Viscous.
Okay, somebody said momentum equation, somebody said viscous, right? Yeah, it's the viscous term in the momentum equation. So the viscous term in Navier-Stokes momentum equation is nu times lambda squared u, where this is the viscosity. All right. So you've already figured out how to write this sort of hidden arcane term, expanding it out into very nice simple derivatives. Fine. Now let's do one more. How about this one? U dot lambda u. Okay, I'm not going to write anything by myself. You will tell me what to write. So, tell me.
The first matrix would be the 3 by 3.
All right, let's put a 3 by 3 matrix. Okay.
That's du dx, du dy, du dz, and dv dx, dv dy, dv dz. Same with the w's.
Fine, next.
Would
Keep
be
going. Yeah.
a 1 by 3
All right.
of u, v, and w.
U, V, W. Yeah. All right, what's next?
It would be another 3 by 1 or 1 by 3.
Yeah. So now we just multiply, right? We're basically done. Let's see. It's a U. Oh yeah, you're supposed to tell me.
U du dx plus u du dy.
Once more.
Oh, plus v du dy
All right.
plus w du dc.
Okay, so the way we got this answer is we take this, multiply that, goes here, plus this times that, goes here, plus this times that, goes here. All right, that's our first element. What's next? Somebody else?
U del v del x plus v del v del y plus w del v del z.
All right, fine. I will not torture you with this one. Okay, so we basically have a 3 by 1, which is a vector. Why did I make you write this one out? What is the importance of this term?
Is that
Have you seen u dot lambda u someplace?
Convective acceleration?
Yeah, this is the convective term in the Navier-Stokes momentum equation. So this is the convective term. In Navier-Stokes conservation of momentum equation. Okay, so what we usually do is we write out the convenient vector form, and sometimes before I'd seen these expansions, I was always confused. Okay, what does this mean? How do I write this out in derivatives? Things I know. So okay, now we know. This whole term expands out into these very nice derivatives. Okay. Fine. So let's quickly write out the full Navier-Stokes equation. So let's see. So Navier-Stokes equations have two components. One is what is the first component of Navier-Stokes?
the viscous term or convective terms? Is that?
No, I don't mean what is the first term. I mean the two equations or the equations that.
Continuity and
Yeah. So whenever somebody says Navier-Stokes, you should always think conservation of mass, which has another name, continuity. We're talking about compressible flow, incompressible flow, which has a third name, which is, well, it's called the incompressibility condition. I don't want to say that. All right, so let's stick with two names, continuity or conservation of mass, which is lambda dot u equals 0. Okay, if we expand this, this is what? All right, now you should be experts in expanding this one. Okay, what should I write?
Del U del X plus del V del Y del G del.
Okay, lambda dot u can be written as du dx plus du dy plus dw dz. Okay, again, if you forget this, go back to taking dot products of nabla and u individually. Right, the next one is conservational mass. No, conservational measure. Do you remember the terms here? This you should remember. Nothing else that we did today you need to remember. So you should remember nabla dot u equals 0 for incompressible flow. And you should remember the 4 terms in here, conservational momentum. So does anybody remember? I will start. So there's a du by dt, but use a vector. And
Plus
U du dy dx u
give it to me in vector.
u dot nabla u.
Plus u dot.
u dot del u
All right.
also 0.
Pressure curve del P by rho
Minus nabla b over rho. And
Plus mu nabla
all discussed
nabla square u.
lambda squared u. You must know this equation. There's nothing, right? There's the advection, diffusion, and a pressure. Okay, and you see now we know how to expand every single term in here. We looked at u dot nabla u. We looked at nabla squared u. We looked at nabla p, right? So this actually is not a single equation, but it's 3 different equations. We can write 3 different equations, one each for how u changes in time, then how v changes in time, and then how w changes in time, right? But if you're confused, u vector is ui plus vj plus wk. Okay, so let's do that. So expanded, we can write this as 3 different equations. All right, so let's see. I will need a lot of space. Del u by del t plus what? Now this is not a vector anymore. We're looking at each component. Okay. So what's the next one?
The first row of convective term that we wrote.
All right. So it's the first row from this expansion, right?
Yes.
So it's this whole thing, right? This is one term. This is a plus b plus c. All right. Fine. Let me copy that down. So this is u del x, b del u del y, plus w del u del z. Okay, that one's done. What's next?
Minus 1 over rho partial p over partial x.
Why? Why is there nothing else in here?
Because in extraction gradients, in y and z is 0.
All right, yeah. So if we think of a simpler explanation,
It's just not changing.
no. I mean, see, there's my point was there's many complicated terms in here. There's u dy, du dz, even just for the x component of velocity. But for pressure, we only do dp dx, not dp dy, etc. Right? Why? Don't think physically, think mathematically, right? What did we say gradient of P can be expanded as? It was this, right? Gradient of P is this. And that's the I, J, K components.
Yes.
Or maybe I misunderstood what you were saying. You were saying the same thing.
I think so.
Okay. So yeah, I misunderstood what you were saying. So yeah, that's the nabla P we are trying to expand. And we know nabla P is just dx, I component, J component, K component. And since we are writing only for the first velocity component, we'll take the I, right? And that's what Kayan said was here, right? I hope I did not confuse anyone. No? Yes? I confused you?
Oh, no, I'm good.
Okay, alright. Okay, fine. Now, last term. What is the last term?
It was mu del F del square U over
Okay, so
del
it's
X square.
there you say this, that. Okay, fine. Am I done?
No, rather two terms.
Partial partial square.
Del square U by del Y.
U by del y squared plus. So that's our last diffusion term, expanded out here. Again, if you don't remember how this happens, go back to our matrices. So this is exactly what we're trying to expand, and we want the first component. First component is the first row. When we write the equation for V, we will take the second row, and then the third row for W. So again, all of this looks very messy, looks very, convoluted, but it's all very straightforward. So is this the full momentum equation?
No, just X.
This is just the x component of the momentum equation. Okay, there's two more we have to write. Let me see. Okay, so let's see. You helped me with the first one. Help me with just the second one, and the third one we will leave alone, right? So let's see, the second component becomes so help me start out here.
Partial V over partial t plus partial V over partial x plus V partial t.
Yeah, so
Change.
again, this took me a while to understand when I was first looking at it. So we're just basically expanding out the u vector in its three components. There's a u component, v component, and a w component. And this is telling us how u changes in time, how v changes in time, how w changes in time. So, and the second component of the convective term, again, we can go back to our convective term expanded out here and copy this second row. Okay, that's exactly what I will do. So there's a u del v by del x. If I make a mistake, stop me. Okay, what's the pressure term?
Partial V over partial
That's the easiest one.
dpdy, alright, and the viscous term,
All U becomes V.
all of the u's get replaced with a v. Okay, so see, it's very similar, but now we're looking at how v is how v evolves in time, right? And then w is plus dot dot dot, right? Dot dot dot. Okay. Perfect. So we've written out this complicated partial differential equation. Now you start to notice some things. If I want to see how V changes in time, it depends very strongly on U and W and this thing called pressure. Okay? That's where all of this issue of, and it also depends on V itself, right? So that's where the issue of nonlinearity comes into play. And that's why these equations do not have an analytical solution, a general analytical solution. And that's also why the only way to get answers for very complicated problems is to do numerics. Okay? There's no other way for the time. Okay, any questions up until this point? All right, so with these Navier-Stokes equations, how many variables do we have? What are the things we are trying to solve for? Four variables. We have four unknowns that we are trying to solve for. What are the four?
U, V, W, and T.
And what?
And T. Time. U, V, W.
Okay, so we have four unknowns.
It depends, I think.
We'll look at that. Four unknown variables that we must solve for. Okay, so you were saying this is U, V, W,
And P.
So T.
okay, there's one answer, T time, there's another answer,
P.
P,
Pressure.
pressure, another answer,
Well, yeah, T is no.
would you like to change your answer? Think about when you solve a very simple ODE, right? dy by dx equals something. You want to solve for y, not for x. X is space or it's t. Right? So you advance in time, but what you're looking for is UVW and
Pressure.
pressure. Pressure is the fourth unknown variable in all of these equations. How many equations do we have?
4.
Somebody said 4. Okay. How 4?
1 continuity, 3 momentum.
I'm sorry, what's 4?
1 conservation of mass and 3 conservation of momentum in 3 different X, Y, Z, and
Yeah, exactly. So 1 conservation of mass and 3 components for the momentum equation. All right. So, by the way, so if this is everything we have done is full 3D, it's completely general. You want 2D solutions, you just get rid of the Z's and the Z's and W's, okay? And it becomes much more compact. Okay, we have 1 conservation of mass and 3 conservation of momentum. From what we have learned up until now, if I just gave you this equation, what would you try? How would you try to discretize this? Anything, any starting point. So, do you know how to discretize dV by dt? Is the question clear or?
guess that was the homework, right?
That was the homework?
No,
Yeah,
not homework, but discretization. So I think we know.
All right, okay. So, all right, then help me do it. So dv by dt I can write as?
V n plus 1 at I minus Vi or ijk at time n over delta t, that equals what was that? Plus u del v del x. So plus u time uij n.
Okay, give me 1 second. So we have ijk because we are working in 3D now. With 1D we only had vi. I was the index in x. Now we have index in x direction, y direction, and z direction, z. All right, so fine. This is a valid discretization of dv dt. Okay, next is u dv dx. You were saying I should write uijk
at time n times what was it, partial. So can write forward.
Should I use center difference? Forward, backward, which one?
On the right side we have a should
Don't jump to the right side here. We're still at the convective terms, okay? You were saying we should use center difference.
I don't say we should use center difference.
All right.
As the center difference is first order. So
Center difference is your second order.
I plus 1, I minus 1.
Yeah.
We can write this.
Yeah, you could use center difference, but remember we had talked about for the advection term, center difference causes a lot of issues.
Yes.
So, what should we use instead?
I plus 1 minus 9.
So it was a what? It was a dv dx, right? So it's you're saying I plus 1
jk
jk
minus bi jk divided by delta y. Delta x, sorry.
Okay, so before we move on to the other terms, there's a few important things here. So you told me it's I plus 1 jk and I jk, right? The j and k do not change. Why? Somebody else?
Because we are moving in x direction.
Yeah, all right, okay. Yeah, we're taking the derivative in x, right? So that's what our term was, dv by dx. So we take difference in x. So that's why he said, take, stay at the same row, stay at the same line and look to your right and left. Okay, that's basically what he said.
Yep.
Now, is this upwinded or downwinded? This is upwinded if u is positive or negative.
If it's positive. Positive? You're going to 1 step?
If it's positive, it's downwinded, because you're,
Alright, so you're saying opposite things. Was right.
I'm confused now. I mean, you're going
you're going plus
1 forward?
right?
Okay.
So that's the direction of the flow.
Yeah,
and you're
positive.
downwinded.
If it's positive, it's positive.
So you're going 1 forward to the right, which means information should be coming from
Left.
It should be coming
No,
from the
information
right.
is coming from
It should be going in a direction that's opposite.
Yeah, okay. So
backward. Yeah, okay. It's negative.
alright. So yeah, if this is correct, if u is negative. Okay? Because you've decided that I plus 1 is more important than I minus 1, which means what happens to me now came from the right.
Right.
Okay, so you would be negative. Okay.
Okay.
So if
I'm confused about left turn right
upwinded if u I j k is less than 0. And yeah, this is a valid expression. If u was greater than 0, you would write I and I minus 1 here. Okay? Alright. So, and the other terms, okay, so let's see. That's just the first term, that's the second term. We have a lot more to go. But let's write the third term, okay? Okay, so.
VIJKN.
All right, so it's V, I, oh, we have an N and an N. Yes. So you said V, I, J, K at N.
Times V, V, I, J plus 1. Okay.
Now you're saying it's J plus 1 comma K.
Minus V, I, J, K. Over delta Y.
Okay, does that make sense to everybody? So now he's taking the derivative in y direction. That's why he went to j instead of I plus 1. Okay. Okay. Upwinded if.
I don't want to mix with up and bottom now, so.
Upwinded
So this
is
has to be negative.
VIJK is less than 0, right?
Yeah, this has to be less than 0 because
Information is coming from
you have biased in the positive direction,
positive direction.
right? No, up, down.
My right is left and left is right now, so.
If V, I, J, K is negative. Okay. And there's a third one, which is W, W, I, J, K, N, and blah, blah, blah. All right, so that's the whole left-hand side. We've just finished the left-hand side of this monstrosity, okay? This beautiful monstrosity. So yeah, so we've discretized the time derivative and the x, y, z derivatives. Okay, let's go to the right-hand side. Okay, so the term is dp dy. Perfect. Rho is a constant, so I will just write minus 1 over rho. Should I write ijk?
Of course not.
Of course not.
No, in homogeneous or not, it depends. It's
Yeah, so that's a very important point.
if you consider it.
Incompressibility just means the density of a blob of a material element does not change. But one blob can have a different density compared to its neighbor blob. Right? So ijk, just to be more general. But as you were saying, if the fluid is homogeneous, where I say everybody has the same density, then you can get rid of the ijk. Computationally, that makes sense. You don't have to store a matrix, a huge matrix for every point or a row. Okay? And most of the simple solutions, the simple problems, you can assume rho is completely constant and equal at all points in the domain. Okay, so then we have a dp dy. What should I do?
People. So we are going to the forward cell again.
Pij plus 1
Minus Pij
minus Pij.
divided by.
Yeah, now we can take central derivatives.
J minus 1 Pij, yes, minus 1 or 2 delta y.
Okay, that's just dy by dx, the second derivative, the second order approximation for the first derivative. Center difference. Okay. Fine. Now that pressure term is done. Let's see what's left. This 3 more discretizations to do. All right, so this is second derivative in x. Let's do just the first one, and the rest you can do on your own. So let's see. Mu times d2b dx squared. So what should I write? Plus mu ijk?
Yes.
Should I write mu ijk?
Yes.
Why?
The same as rho you did for
If rho depends on ijk positions,
Yeah.
the viscosity can change due to compressibility too.
Yeah, exactly. Nu depends on rho, right? So you would, to be the most general, you would write ijk. But again, for most computations that you deal with, unless it's a very exotic computation, this is like, if you do compressible flow or non-Newtonian fluid, you can assume that nu is constant throughout the domain. Okay, fine. And then the first term was d2b by dx squared. What should I write?
Can you just
Then you put an n and an n. All right. What did you say?
can you keep the paper a little bit more
Oh, yeah.
that we can see?
All right.
Okay.
d2b by dx squared. Right.
I plus 1 minus 2i plus minus I minus 1 or x squared. Yeah.
Over.
Delta x squared.
Yeah. So it's just I plus 1 minus 2i and I minus 1. In j and k, you do not move. Okay. At this point, some of you might not entirely be able to visualize what these I, j, k's mean. So we will do a very simple 2D grid. Okay. Now, all right, fine. You have helped me discretize the full equation just for the second element of the momentum equation, right? So just the second component of the momentum equation. Can we solve this using the methods we have seen? So we know how to do the over dt, we have done the upwind, we have done the diffusion here. Can I solve this now? Can I write a MATLAB code? You're saying no, why?
No boundary conditions?
All right, so yeah, before you start solving, I have to give you initial conditions and boundary conditions. Assume I give you those two things. And then, would you just start writing code?
Of course, we have to expand for other terms because unknowns, we have more unknowns.
Yeah, so we have done one equation. There's two more equations, we would have to do something similar. All right?
Yeah, after that, yeah, and with boundary condition, I think we can write the code.
Okay, so one opinion is fine. If I give you boundary conditions, initial conditions, and we discretize the remaining equations, we should be able to solve it. What was another answer? There was another one. All right, so let's see. If I want to go from step n to step n plus 1, I need all these values at step n.
Yes.
Fine. You can use that with the velocity initial conditions I will give you. Do you know the pressure? I never gave you the pressure, right? I will just give you at x, y, z, this is what uv, w looks like.
This is why we solve the pressure pulsar equation instead of momentum and give us an initialization depending on the velocity.
Okay, so one answer is that's why we solve the pressure Poisson equation to get these p's first, and then we can solve this momentum equation. Yeah, that's a valid approach. We will see that we do something similar, but not exactly, and I'll tell you why. Okay. So the first thing we need to do is we need to compute this P from the things I give you, which is U, V, and W. In incompressible flow, before incompressible flow, in general, do you know how pressure is? Do you know what the equation of state is? So maybe you have seen this probably in chemistry, maybe
We
also.
know equals to RT.
Yeah, probably even in turbulence. So equation of state is just, as you were saying, it's P equals rho RT. Temperature, this is a constant, and this is a density, and this is the pressure. Okay? This comes from chemistry, and it's a very simple expression. But in incompressible flow, we never ever mention temperature. That's one special thing about the incompressible flow. Temperature actually becomes decoupled from the flow. Okay? So pressure takes a special form. It's in the solution of the Navier-Stokes, the pressure actually enforces continuity. Okay? And we will see how that happens. It's called the pressure projection method. To get there though, we have to first figure out what the pressure Poisson equation is. Okay, since you mentioned this, do you remember what it is? Yeah, looking at you.
By me.
Okay. So the Poisson's equation is basically nabla squared something equal some f of x or y or z. Right? This is a very difficult equation to solve. It's very simple in form, but it's very, very difficult to solve. Think of it physically, right? If instead of pressure we're talking about temperature, if you remember the solution, the steady state heat equation is the Poisson's equation. So if we are talking about temperature, I will give you the second derivative of temperature at every point in the domain. Tell me what the temperature is. Okay. So if so if I have a plate, I will tell you that I will give you the second derivative of temperature at every point. Oh, I wish I had drawn a smaller plate. So let's see. Let's take temperature. Let's take temperature, example of temperature. Tx comma y. Okay. So I give you del 2t lambda squared t, which is just del 2t over del x squared del 2t over del y squared. And I ask you to give me okay, so is the solution, is the problem clear in your head? It's like, I don't tell you anything about the temperature, but I tell you, aha, the second derivative is some number. Okay, what is the temperature? You tell me. So, how would you do it?
Integrate twice.
You would integrate twice. Yeah. But there's a problem there. Okay? If you integrate, you have constants which are unknown. So there will be constants which, so if I don't tell you anything besides this information, what will you tell me?
You cannot solve it.
You cannot have a unique solution. For that, you need to ask me to give you some boundary conditions. Right? If I tell you, okay, temperature along this whole side is fixed at 100 degrees centigrade, then you know how to get a unique solution. Okay? Okay, so first thing is you should ask me for okay, fine, I gave you the boundary conditions. What would you do then? Remember, we're talking numerically. Forget about integration now. Okay? So I give you at these 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 25 points, I give you the second derivative. What is the discretized equation you will start writing down? I heard the centered, yes, yes.
Central.
Centered, okay, so I should write down, what should I write?
Ti plus 1 minus 2 ti plus ti.
Should I write J's? This is a 2D problem, right?
This is a 2D problem, so it has j too.
J plus 1 or J minus 1?
J.
J.
X squared. Delta x plus this thing, just change anything, is j plus 1 I minus 2 t.
Yeah. Is that correct? Did I make a mistake? No. All right, very good. Correct. Over.
Delta y squared.
Okay, then?
That equals to what? What's the piece?
Say I give you this as a f x y, x y, right? Yeah.
N equals to the value you found.
Yeah, so it would be f I, j. Right? If I give you a function, you will just evaluate it at these node points. I give you the individual numbers itself, you would have the values at I, j nodes. Okay? Do we know how to solve this? What is known? What is unknown?
We know with ij's, but in order to find ij minus 1,
We know what?
we know the actual, we start from a point, but when we start a point, we don't have ghost cells that we don't know. In order to find it, we will use backward.
We don't even know the Tij. I think it's six unknowns.
So, see, what I said was I will only give you the right hand side. Right?
Yes.
I will tell you what the
Boundary
oh,
conditions.
sorry, this is not F. This is F, right? This is F.
This is
Yeah, sorry. So I told you I will only give you the right hand side. And you give me the temperature. I only give you the second derivative, you give me the temperature. So you actually don't know any of these t's. Nothing in here is known. The only thing you know is this one. Okay? So we have 1, 2, 3, 4, 5, 6 unknowns. How do we solve this? think about that. Before that, I will just write out the cross, okay? There is an answer, okay, so let's go ahead. Go ahead.
So we will take some initial conditions.
Can you push the button? I can't hear you.
So we will have some initial conditions and we will write this in terms of t I comma j, and then we will start iterating until we get a solution which doesn't vary anymore.
Okay.
So
what should the initial condition be?
well, you can take them as you like.
Yeah, exactly. So what he's saying is, you know, I don't know what the solution is, so let me start with an assumed distribution for t in this plane. Okay? And I know the t should satisfy this equation. So I will start with an unknown, with an initial guess, and slowly I will iterate towards the correct guess. But there's another way. You don't need to start with a guess. Okay? Do you remember in implicit time integration, we had the same issue, right? There were unknown variables, 3 of them in the same equation that needed to be solved for. So how would you do that? Do you see what I mean? If you remember in an implicit solve, we would have 3 unknown t's at time level n plus 1, and we didn't know any of them. But we didn't start with an initial guess, right? At that step, we would have to solve this huge matrix system. So this, again, becomes a matrix system solve. Does this make sense? Yes? So yeah, but these are 2 completely valid ways. You can do a direct solve of the matrix system, or you can do an iterative solve. Take an initial guess and slowly iterate. And these 2 are methods that are used in practice. That's exactly what the iterative matrix solvers do. The conjugate gradient and the GMRES, which we were looking at in MATLAB. That's exactly what they do. They take an initial assumed solution, slowly they iterate. Okay, so fine. Before we form the matrix, let's look at what's happening here. So what's happening is I have my grid, okay, and let me look at one particular point. So this is I, j. Okay, which are the important points here for solving this? The Laplacian, basically. So, do you understand what I drew here? Sometimes I forget to explain. So, is it clear?
Yes.
All right. Yeah, so it's just this whole plate. I'm looking at one small section of it, okay? And this node, general node, is called ij, right? What is this node?
I plus 1.
A plus 1, comma? J. I minus 1, comma, j. I, comma, j plus 1. This is I, comma, j minus 1. Okay? Should I take more? Are these all I need? Should I take this one?
Oh, no.
No, yeah, because in my equation that one doesn't show up. You know, I minus 1. In some other equation or some other discretization, that might be important. But the one we picked, that's not important right now, okay? Fine. So what this is saying is, if I want temperature at I, comma, j, I need to know data at all these 4 points, right? So sometimes it's called a Laplacian cross, I think. So yeah, and see this stencil, this is called a stencil. This stencil is basically what will be used for all points. When I move to the next point, this whole stencil moves with me, and then, then we have a new neighborhood. Okay? Fine. So last step, and we will stop after this, is to write this whole thing as a matrix solve. So something like AX equals B. Okay, so let's see. There will be this big matrix, and there will be an X vector. So let's fill out the X vector. What should I put in here? What goes in this vector? The
IJ.
T. This.
AX.
This is a general AX equals B solution, right?
So is X and Y? What is that?
So you would have a T1, comma 1, right? Then there's a T, which direction should we go in? We should go in, fine, let's go 2, comma 1. So the problem now is we are in 2 dimensions, so this, okay, in 1 dimensions it was easy, right? We had a rod and we would go from I equal 1, 2, 3, 4 to the n. But now we have to go in 2 directions. We have to go in I and in j. And all of these 25 different t's, I can basically write as one long vector, right? That's what I'm doing here. So, okay, then we write out T4, comma 1, T5, comma 1, and then what comes next? T1, comma 2, T2, comma 2. Okay, this might take a bit. Okay, okay. So these matrices are huge. So this might take a bit of time to sink in. So let's go slowly here. And we have 2 minutes, so we might finish this next time. T1, comma 1, 2, comma 1, 3, comma 1, 4, comma 1, 5, comma 1. This means I'm taking the first row. That's the temperature on these nodes. Once I'm done, then I start with the second row, which is T1, comma 2, 2, comma 2. So I will have 25 elements in here, 25 t's, unknown t's, because I want to solve for 25 different nodes, okay? And imagine, just for this very simple, very coarse problem, what is the matrix size? This is 25 by 1, this has to be, if it's a square matrix.
25 by 25.
Yeah, this will be a 25 by 25 matrix. Just for this very simple toy problem. Imagine if we are doing 100 points